Hello, welcome to the video on the first law of thermodynamics. This video is roughly split into 4 pieces. So the first is the top half of this page, where I just go over heat, work, and internal energy and the first law of thermodynamics. Then we'll talk about thermodynamic processes, some common ones. I haven't drawn them in here yet. We'll do that together. And then we'll talk about heat capacities in a little bit more detail. And then we'll talk about heat engines for the last part. So these are, so I'm roughly going in the order of the book. So sections 3.2 to 3.3, section 3.4. This should read section 3.5, heat capacities. And then section 4.2 on heat engines. This will all be covered on your next homework assignment. Okay, so zoom in. Okay, so the first law of thermodynamics says that the internal energy of a system can change 2 different ways. So this right here is talking about just the total energy inside some system. So you define something, and the interesting stuff here is gases. So suppose you have some container, and our system oftentimes is the gas that's inside the container. And we want to keep track of how much total energy it has in the microscopic motion of all the molecules moving around translationally, maybe rotating, maybe vibrating, all that is energy. So just before I forget to point it out, the different books label this total internal energy differently. Some books use the letter U for this internal energy. Some books will call internal energy and thermal energy the same thing. So there are differences in that, like, maybe internal energy could also include some chemical energy or something that's not thermal energy. But because we're not talking about chemical bonds being broken, we're going to use them synonymously. So thermal energy, internal energy for us is the same thing. So there are 2 ways, and this is if you had to sum up thermodynamics in one sentence, this is it. There are 2 ways that you can change the internal energy of a system. You can heat it up, or you can do work on it. Okay. Now, the minus sign is kind of funny here. So if you heat up, so suppose you want delta U to be positive. You want to add energy to a system. You could heat it up. So in other words, you put positive heat to the gas, so delta Q would be positive. Or you could do work on the gas. Now this really depends on the textbook that you have for what is meant by W. So your OpenStax book follows a convention used mostly in physics and not in chemistry, where W is the work done by the gas, and not the work done on the gas. So this word right here is really, really important. Work done by the gas, not the work done on the gas. So if this was defined to be the work done on the gas, there would be a plus sign. I guess in order to explain this minus sign, I kind of have to talk about this formula right away. A gas, if it expands, so you have some gas in a container. If you allow it to expand, so it changes its volume, it increases its volume, it's doing work on the surroundings. So pressure is the gas pushing against the container. And if the container moves outward, while the gas is pushing outward on the container, then the gas is doing positive work on its surroundings. So work is a transfer of energy. If the gas is doing work on its surroundings, it's getting rid of some of its internal energy. In order for it to expand, it needs to use up some of its energy. Okay, so this is why if a gas expands, its internal energy goes down. That's the main idea here. So you'll notice that this definition for work done by a gas is positive if the gas expands. So the work done by a gas, it's integral of, so you're used to integral of f dx for work here. So if I do this magical thing, I divide by area and I multiply by area, this a dx becomes like a volume, and the force per unit area becomes like a pressure. So integral of, so work, which you're used to seeing it this way, is the same thing as integral of p dv. So pressure times the volume, and really the integral of P dV, the area underneath the pressure as a function of volume, gives you the work done by the gas. And if positive work is done by the gas, then the gas loses that energy. Okay, and this is all summed up with the first law of thermodynamics. So one thing to emphasize right away is that if a gas expands from some initial point to some final point, it can do it in a variety of ways. So I drew one path here, but another one could be, going like this, from the initial point to the final point. And these two paths have different areas underneath them. So the work would be different in those two cases, which is this statement right here. Delta W is a path-dependent function, or quantity. You can't even call it a function, actually. Well, I gotta be careful with the words here. Work is path-dependent. It depends on the path in the PV plane. Internal energy, though, is path-independent. Okay, so delta U only depends on the initial and the final points there. So if the internal energy is path-independent and the work is path-dependent, that means the heat added is also path-dependent. Right? If delta U is fixed for these initial and final points, then as delta W increases, delta Q also increases as well to offset that right here. Another thing to point out that I'd like to point out is that a path, P is a function of V, a path in the PV plane, is reversible. So in other words, in order to draw a path right here, that means you have to have a whole bunch of points that are well-defined. And each one of these points has a well-defined pressure and volume. So notice that just to draw a point in this plane here, this PV plane, there has to be some well-defined pressure, well-defined volume. So anytime you see a path on a PV plane, it means that the process is done reversibly. And reversibly means slowly. It means very, very slowly, quasi-statically. A lot of these terms are used interchangeably. It means this process is done so slowly that there's a well-defined temperature, pressure, volume at every intermediate step along the way. Okay, so we're going to talk about also irreversible processes when we talk about entropy later. But for now, anytime we draw a path, that means that there's a reversible process. Okay, for irreversible processes, you can't even draw a path on the PV plane. And then finally in this section is a reminder from last week about how you might compute the internal energy. So this is NCV delta T, or in terms of the number of degrees of freedom, D, it's D over 2 NR delta T. So if you have the path in the PV plane, the work is easy to calculate. Delta Q is not easy to calculate for any general path. We'll talk about a couple where you can calculate it later, but in general, you can't calculate P as a function of V as easily as you can the work, because the work, you could compute that for any function, P as a function of V. You can calculate that integral. Even if you can't do it analytically, you could numerically approximate it. So you calculate delta W, you can calculate the change in internal energy, and then you can infer from the first law of thermodynamics what delta Q is. So a lot of times that's the order in which how easy these things are to compute. Delta U is the easiest probably, then delta W, then delta Q. Okay. Next is a section going over some common processes along with some definitions. Okay, so I drew an initial point here in the PV plane. Now I can imagine changing this system in a variety of ways, and all of these are going to be reversible. Again, just because I'm drawing a path on a PV plane, that means they're reversible. We could heat up the gas at constant volume. Okay, this is called isochoric, or constant volume. So isochoric means heating up at constant volume. Another one would be heating up at constant pressure. So this would be isobaric. Iso means same, bar for pressure. Same pressure, ic. Core is maybe harder to remember. Core means volume. that one's not as easy. Another one is isothermal. So isothermal means same temperature. Isothermal means constant therms, constant temperature. And so remember that pressure times volume is proportional to temperature. So PV equals nRT. We're not changing the number of moles. We're not changing the gas constant. So constant temperature means that pressure is equal to a constant divided by V. Okay, so in other words, an isothermal process is a hyperbola. Hyperbola in the PV plane. Right? Pressure, this is the vertical axis, is equal to a constant divided by something on the horizontal axis. So let me draw, I guess that's a hyperbola. So it should be the case that if I double the volume, I have the pressure, right? That's what a hyperbola is all about. So this one is isothermal. And I want to point out, this is important. Internal energy is a function of temperature alone. So taking a look at this equation up here, delta U is proportional to delta T. If temperature is constant, delta T is 0, and that means delta U is 0. So isothermal also means that U is constant as well. So isothermal means constant internal energy, and it also means constant temperature. It means both of those two things. So hyperbolas are nice ways of classifying points on the PV plane, in the PV plane, right? So the higher the hyperbola, in other words, the higher the temperature, the higher this hyperbola is. So like if I drew a hyperbola way out here, that has a higher value of P times V, that has a higher temperature, higher internal energy. So what am I saying? I'm saying that I can read off, so this is an isochoric process where, based on the direction of the arrow, I drew this path going in the direction of increasing internal energy, increasing temperature. So that's how I know that, like right here, we're heating up the gas. So for isochoric, there's no work done, right? The area is 0 there. From the first law of thermodynamics, if there's no work, delta W is 0, then the heat is the same as the internal energy. The internal energy goes up, Q goes up. Okay. Isobaric is a process where delta W is positive, work is being done by the gas, so that internal energy goes down. It should go down if the internal energy was changing only because of work, right? The gas is expanding, it's losing energy, but we're jumping onto a higher isotherm, right? As this gas is going to the right, we're going to higher and higher isotherms. So that means, again, from the first law of thermodynamics, and this is going to control a lot of our thinking in this chapter. We're always going to go back to this first law of thermodynamics. If delta W is positive, but delta U is also positive, then that means the heat added must be positive as well. And not only is it positive, but it's bigger in magnitude than the work done by the gas. Because overall, when you add up delta Q and delta W and subtracting off delta W, it has to be positive. So isochoric and isobaric heatings go in the direction indicated. Isothermal, if delta U is 0, then delta Q is equal to delta W. So what that means is if I heat up a gas at constant temperature, delta Q is positive and the heat and the gas expands. So the gas expands, and every amount of energy that I give the gas in the form of heat, it's using that energy to expand. So if I give it 20 joules of heat, it's doing 20 joules of work on the environment. The work done by the gas is 20 joules, and those two will cancel out in the first law of thermodynamics. And so delta U would be 0, which is what it means to ride along one of those isotherms. So if a gas is expanding, and it's expanding the direction indicated because the volume is going up, right, from some initial volume to some final volume. So if the gas expands isothermally, then you have to give it heat, but it's using the heat to expand. It's using all that heat just to expand. And so there's no overall change in temperature, there's no overall change in internal energy. The final process that we want to draw here, what color do I want to use here? The final process is adiabatic. So all of these processes involve heat exchange. Delta Q is non-zero. There is a process where Q is 0, and this is what's called an adiabatic process. And I drew the direction of the arrow is such that it's an adiabatic expansion. An adiabatic expansion has delta Q equals 0. So adiabatic has delta Q equals 0. So P times V is not constant for this process, but what is constant is P times V to the gamma is a constant. So in other words, P initial, V initial to the gamma equals P final, V final to the gamma. So, or you just might see this written as P times V to the gamma equals a constant over the whole path. So we'll talk about what this constant gamma is in the next section, but it's called the adiabatic constant. And gamma is bigger than 1, which means that these adiabats are steeper than the isotherms. So whenever you have an adiabatic expansion, you go down in temperature. Okay, when a gas expands and there's no heat transfer, then it's using up some of its energy to expand. And so its internal energy goes down, its temperature goes down, which is why we're jumping onto a lower isotherm. Okay. So adiabatic, so all of these are reversible, which, ideally they happen infinitesimally slowly, they're quasi-static. If something happens quickly, it's most likely adiabatic. So here we're still assuming it's reversible, but a lot of times if something happens quick, then there's not enough time for heat transfer. The work can be transferred almost instantaneously. Sometimes heat needs some time to transfer. We talked about heat transfer mechanisms and how fast they could happen. So basically, if you're told that something happens quickly, it's probably adiabatic. The next section revisits a formula in calorimetry. So for solids and liquids, we didn't have to worry about the volume changing. And so for solids and liquids, let me just write here, solids, liquids, we wrote delta Q equals m times lowercase c times delta T. Now for gases, delta Q equals, well, it depends. So you can't just write one formula that always works for delta Q, because remember, delta Q is path dependent. There's a couple paths, though, where you can write the formula very similarly to this. So the most common one is to write it almost the same exact way. That's this one right here. So if your gas isn't changing volume, and this is basically what we were doing with solids and liquids, because for solids and liquids, the liquid or solid doesn't change its density very, very much when you heat it. So constant volume, delta Q is equal to, so now we're talking about molar heat capacities instead of heat capacity per unit mass. So before with this MC delta T, the C had units of joules per kilogram Kelvin. But now we're going to talk about joules per mole Kelvin, molar heat capacities. So we use capital C's for this. This C right here is a capital C sub V. So we do number of moles, not kilograms, but number of moles for the gas times capital C sub V, which is energy per unit mole Kelvin. And the subscript is telling us that it's the molar heat capacity at constant volume, which is different than the molar heat capacity at constant pressure. So CV and CP are not the same thing. Delta Q equals N CV delta T. So here, the way I drew these arrows, this is the initial temperature, this is the final temperature. By looking at the hyperbolas, remember what we learned last time, by looking at the hyperbolas, we see that we're going to a higher temperature. We're going to a higher isotherm. So we're going up in temperature, we're adding heat. This is going to relate delta Q and delta T for us. But this equation is only for constant volume, so only for vertical lines. This equation is only for constant pressure, only for horizontal lines. Okay, any other process would have a different formula for delta Q. For the isothermal case, delta Q is non-zero, but there is no temperature change. So you couldn't even write a formula like delta Q equals something times delta T, because they're definitely not proportional to each other, right? In that case, delta T is 0, but delta Q is non-zero. But these two are common. So these are molar heat capacities at constant volume and constant pressure. And the constant volume one happens to be equal to delta U, because delta Q and delta U, only for this special case where there's no work, only for vertical lines, heat and internal energy are the same thing. However much energy in the form of heat you add to it, that's the change in internal energy. Okay, so this formula you can use no matter the path. And for a constant volume process, it happens to be equal to the delta Q. Okay, but delta Q can be different for other processes. These two are related by this formula right here. So Cp is Cv plus R, the gas constant R. Okay, and this is just, to go to the same hyperbola, you would be having the same change in internal energy here for the two starred paths, right? For the isobaric or the isochoric. So that if you set those delta T's equal, and you could solve for the work done under this one pretty easily, right? That's just the area of a rectangle right there. So you can prove that this formula is true, Cp equals Cv plus R. And it makes sense that it takes more heat. So notice what this is saying. For a given delta T, it takes more heat to heat it up at to heat a gas up at constant pressure than it does to heat it up at constant volume. And the reason for that is some of the heat that you're giving the gas is being used as work. Remember, the gas is expanding, so it's losing some of that energy in the expansion. But at constant volume, it's not losing any of that energy. So you don't have to give it as much energy in the form of heat. So this adiabatic constant that we talked about up here, this is the ratio of heat capacities. This is how it's defined. So Cp is always bigger than Cv, which means gamma is always bigger than 1. And gamma is, the most it is in 3 dimensions is 5/3. Okay, so this is for a monoatomic gas. So there's a relationship between the value of gamma and the number of degrees of freedom. If there are only 3 degrees of freedom, for like a monoatomic gas or a diatomic gas at really, really low temperatures, then the value of gamma is 5/3, 1.67. Then as the number of degrees of freedom goes up, the adiabatic constant goes down. So diatomic gas at room temperature is about 1.40. At really high temperatures, diatomic gas is 1.29 for the adiabatic constant. Okay, so this is a reminder that Cv is related to the number of degrees of freedom, and so you can derive these fractions right there. Okay, the last part that we need to know about is heat engines. So schematically, so we're going to divide looking at this into 2 pieces. So let's look at on the left first. What the point of a heat engine is to take heat and convert it into work. Right? So your car engine works because we heat up a gas-air mixture, and we use that. It gets really hot, and we can use that to make the transmission start turning around. And there are other parts of the car, but to make the car go. So we want to maximize the work output given how much heat that we started with. So this circle right here, so this is schematically like you have a hot thing. So heat is going into your system. That's what the red thing is. It's your working substance. So it could be gas, gas-air mixture. Could even be a liquid, but we're going to focus on gases because we're going to relate this to PV diagrams. That's the energy going in, is energy in the form of heat. You can do some useful work out of. You can get some useful work out of that heat energy, and then there's some waste heat. So we'll talk about the fact that you can't convert all of it to work when we talk about the second law of thermodynamics. But we want to maximize this efficiency. We want to for a given amount of heat that we're putting into the system. That's our starting amount of energy. We want to maximize the work output. Okay, and just from conservation of energy, we have this relation right here. The energy that we started with is equal to the energy that we wind up with. So either useful energy or waste heat. In terms of a PV diagram, so now looking at the right-hand side here. In terms of a PV diagram, a engine is a cycle. So a cycle is a closed path in the PV plane. Closed path. Engines are paths that go around in the clockwise direction. And actually, refrigerators go around in the counterclockwise direction. So we're not going to talk about fridges, but those are also pretty interesting. Okay, so we're drawing the PV diagram of the working substance. And so anytime energy flows into the working substance, anytime Q is positive, that's contributing to QH. That's part of QH. QH is any heat that's delivered to the system. So here you have to break up your cycle into all of the different paths and see which ones have Q positive. So look at this definition right here. QH is you add up all of the Qs that are positive. So in this case, we have an isochoric heating, step 1, and then an isobaric heating, step 2. So you would add up Q1 plus Q2. You would totally ignore Q3 and Q4. Those are part of the QC right here. Those are heats that are leaving the gas. And then the work output in one cycle is the area enclosed by the cycle. So in this example, it would be the area, it would be the work done in step 2 plus the work done in step 4, but the work done in step 4 is negative. So it will partially cancel out, and what you're left with is the area inside the cycle. So we'll talk about, in class, we'll talk about some common types of engines. And by different types of engines, we mean different cycles in the PV plane. So like for your car engine, you're going to have constant volume processes and then adiabats connecting these, just because adiabats happen very quickly, not enough time for heat exchange. And constant volume is easy because you can trap, you could force your container to be some finite size. So a lot of times just the shape that these take on depends on what limitations you have when you're constructing your engine. Okay, I know this is a lot of info on both of these pages, but this was just to give you an overall view of what the first law of thermodynamics is all about. So you'll get much more practice with this on your problem set and in class.